Hello guys, in this video we are going to change a little bit the topic. We are going to see simple orbital maneuvers and the idea is to work with functions, and in this case we are applying many mathematical ideas. So I think it's a good example. Probably some of you can think, okay, so what? Simple orbital maneuvers. I'm not interested in these things. But I'm just trying with these videos to offer you a possibility to see how these ideas of mathematical functions, derivatives, and increasing functions, decreasing functions are applied. Okay, we are going to focus on simple orbital maneuvers. It's in a practical way. Okay, I hope you like this video. Which are the objectives? We are going to try to understand what is required for to make an orbital to make an orbit change, and we are going to see how to do that. We need to introduce several key ideas. Okay, one is the specific momentum of an orbit. It's going to be easy. Okay, I'm not going to mess. I'm not going to enter the field of physicists. I'm just going to see it from a mathematical point of view, from the point of mathematics functions, depending on something. Okay, that is I think it's a in my opinion, it's a very beautiful application, and this way you can just see something that is sorry, something that can be applied in real life. Okay. We need, what is the requirements? The requirements are a little bit of calculus, a little bit of knowing how to calculate, how to simplify expressions, what is the definition of a function. I'm trying not to give you much more information than you need. Okay, so let's continue. First thing. This is just data that you need to remember. You know, when you are going to do exercises, these are the information you need in order to solve any calculation. Mu, let me recall, it's the standard gravitational parameter. The second one, RT, is the radius of the Earth, and G0 is the acceleration of gravity at the sea level. But as you see, I'm using the units in kilometers. The first one is in kilometers cubed divided by seconds squared. The distances, I'm going to use kilometers. We are not going very far from the Earth, so kilometers is good. And finally, be careful because I guess you are used to this number in meters per second, 9.81. But since we are using kilometers, remember 0.009981. Okay? So, an orbit. Let's suppose you have a main body. You have satellite orbiting the Earth. Let's suppose it's the Earth. It's good to suppose that the main body is the Earth because I'm making this important. I'm taking mu as the standard gravitational parameter of the Earth. Okay, so be careful if we are orbiting around Mars, for example. Mu should be the one corresponding to Mars. Okay, in this case, the one you see on the screen is the Earth standard gravitational parameter. Okay, so let's suppose you have the Earth and a satellite orbiting the Earth. Okay, the specific angular momentum is defined as the cross product of the vector, the position vector times the velocity vector. Okay, this specific angular momentum is going to be always perpendicular to the orbit plane. As you imagine a satellite orbiting the Earth, okay, in an elliptical, for example, in an elliptical orbit or circular orbit, whatever you prefer. Okay, this orbit is contained in a plane. This is called the orbit plane. So the angular momentum is defined as the cross product of the position vector that is in this plane, orbital plane, and the vector velocity that is also in the orbital plane. So the specific momentum is always perpendicular to the plane of the orbit. Okay? It's just by definition of the cross product. And it's how do I calculate the cross product? It's very easy. Just review the textbooks and also the notes of the subject because you are going to find the definition. But it's not what I want you to apply here in the video. Okay? So another thing. the velocity vector can be expressed in two components. One is called the perpendicular component and the radial component. The radial component is if you continue the vector that joins the satellite with the Earth, if you continue that, this is the radial component, and perpendicular to this radial component is the perpendicular component, okay? But, okay, I'm messing too much with these ideas. Okay, the key point of these orbital maneuvers is that the angular momentum, the specific angular momentum of an orbit, is constant. Okay, that is the key part of this slides and video. Perfect. If h is constant, I'm not going to work with vectors. I want to work with modulus and magnitudes. So what do we have here? If we are orbiting in an elliptical orbit, we have two important numbers. Which are these numbers? Let's suppose this is the Earth, the elliptical orbit goes like this, and the farthest point to the Earth is called the apogee, and this distance is called the radius of the apogee, and this is denoted by r sub a. At the point of the perigee, remember, this is the Earth, this is the farthest point of the ellipse, this is the apogee, this is the radius of the apogee, and at this point it has a velocity. This velocity is called VA, or V sub A. This is the speed of the satellite at the apogee. What is RP and VP? This is the other point of the ellipse, the other important point. If this is the Earth, this is the farthest point, the ellipse has the closest point to the Earth. This is the perigee. The distance from this point, the closest points to the Earth, to the perigee, is called the radius of the perigee. And at this point, the satellite has a speed called VP. If you solve from these equations, remember that I didn't change h because h is constant all the time. So I can solve for the velocity at the apogee here, and I can solve the velocity of the perigee like this, using the specific angular momentum. And you can think, okay, I don't even care because I don't know the specific angular momentum. I need to calculate first the specific angular momentum in order to know the speed of the satellite at the perigee and apogee. Yes, you're right. Okay, but, okay, we will provide a way to calculate this h. Okay, important things. We need the radius of the apogee and the radius of the perigee in order to calculate the speed. Then, we have these formulas. They are really known formulas, just don't worry, I'm not using very complicated formulas. If you know not the radius of the apogee and the radius of the perigee of the orbit, but you know the major semi-axis and the eccentricity of the ellipse, then you can know the radius of the perigee and the radius of the apogee. And putting these two things together, I have this information, that the eccentricity can be written as the radius of the apogee minus radius of the perigee divided by the radius of the apogee plus the radius of the perigee. Perfect. So, the idea is, using the formula, the conic formula for the ellipse, don't worry about the middle steps, you can find an expression for the specific angular momentum only in terms of the things we know from the orbit. Okay, and this is the key point of another key point of these slides is, do you know how to calculate the angular specific momentum of an orbit? Yes, you only need the radius of the apogee and the radius of the perigee, apart from the standard gravitational parameter that you are seeing perfectly here. Okay, but this is a really nice way to calculate the magnitude of the specific angular momentum. You only need radius of the apogee, radius of the perigee. Perfect. So, how can I change speed in a simple orbital maneuver? Delta V, it's the measure is the variable we are going to obtain in order to know how much I need to change speed in a point in an orbit to change a little bit the orbit. Okay, and the expression of this delta V, the proof is very long, but I'm just providing the final formulas, okay? As you can see, the delta V is only calculated in terms of the radius of the perigees and the radius of the apogees. And you can ask me, okay, but you have written there RP to RP1. What does this mean? Why do you have two radius of perigee? It's a good question. If you just realize this, we are in the right direction, okay? So, let me show you something. This is the key point. This is one of the most simple maneuvers in space. What I'm trying to do in here is, you are orbiting in this path, in this orbit. The black one, I know, it's not well seen, but I promise you this is black. This is the radius of the apogee, the farthest point. This is the radius of the perigee of the original orbit. What we are trying to do is to increase the radius of the perigee a little bit. Okay, so in impulse maneuvers, when in the place you make the impulse, you are going to pass through this point again. Okay, you can complain with what I have just said, but if the impulse is very short, for example here, we are going to pass through this point again. I just modify the orbit. Okay, perfect. But if I apply the impulse here, then the new orbit is this one, as you can see. And we will come back to this point exactly. Applying an impulse in here makes the perigee increase a little bit. Okay, by the way, we are moving in this direction, okay? So the impulse I'm doing is just exactly in the same direction the satellite is moving. Okay, so guys, perfect. We have the radius of the apogee for the initial orbit, the black one, and the pink one, the final orbit. The radius of the apogee is exactly the same, and we denote it like RA. The radius of the perigee of the initial orbit is RP1, but the radius of the final orbit is what we have called RP2. So, perfect, we got everything we need. With this information, we got everything. I can calculate how much impulse I need to change from the black orbit to the pink orbit, okay? And let me go back 1 second, because this is the exercise I wanted to calculate. Okay, we have a satellite with a mass of 2,000 kilos orbiting around the Earth with a major semi-axis of 8,778 kilometers and an eccentricity of 0.3. That is it's not a cycle, it's like an ellipse, okay? And we want to increase the perigee by 90 kilometers, not so much. And we also have the specific impulse of the satellite. All this information will help you to solve the problem. How are we going to solve the problem? Okay, perfect. First things first, the specific moment of the orbit were calculated based on the radius of the apogee and perigee. Okay, so we need to calculate the radius of the apogee and perigee of both orbits, the initial orbit, the black one, and the pink one. Okay, so let's start with the first one. The radius of the apogee is always the semi-major axis times 1 plus the eccentricity, and the radius of the perigee is always the semi-axis times 1 minus the eccentricity. This is formulas coming from mathematics. It's my mistake. I could have provided you with the radius of the apogee and perigee directly, but okay, I'm just since we are here, let me introduce two more formulas. Okay. By the way, this is the radius of the apogee, this is the radius of the perigee. If you replace these values in this formula, what you obtain is the specific momentum of the initial orbit, the black one. Come on, now let's calculate the specific momentum of the second orbit, okay? The radius of the apogee of the second orbit, remember that this is the pink one, the radius of the apogee is exactly the same. So when I replace here, I'm just going to put the same number. But the radius of the new perigee is the old radius of the perigee plus 90 kilometers. So this is the radius of the second perigee. If you replace in this formula, you obtain the specific momentum of the second orbit. Do you want to calculate the change in speed? Perfect. Then we can just calculate the delta V with the formula or the way I show you here. Remember that the speed at the apogee is the specific momentum divided by the radius of the apogee of the second orbit, and minus the specific moment of the first orbit, the black one, divided by the radius of the apogee. Why I'm dividing by the radius of the apogee? Because it's the place where I am applying the impulse. Let me go back 1 second. Here, I'm applying the impulse on the apogee. So that is why I'm dividing by the radius of the apogee. What I'm doing in this exercise survey is trying to calculate the change in speed from the initial orbit to the final orbit, okay? So if we calculate the values, I have everything here, the specific moment of the first orbit, the specific moment of the second orbit, and if you replace the values here, you obtain a change in speed of 0.02. The question could be, okay, is this much or not? Remember that we are talking about kilometers per second, so it's a lot. But how much fuel I'm going to waste in this maneuver? Waste, I'm going to use. I'm not wasting fuel. Okay, so the mass is calculated, or the change in the propellant mass is calculated with this formula. I only need to replace the initial mass, the delta V already calculated, the specific impulse was given in the beginning of the exercise, was 300 seconds, I guess. G0 was the acceleration of gravity at the sea level. So if you calculate and replace everything in the formula, what you obtain is 16 kilos of propellant will take you to change the perigee of an orbit only 90 kilometers. Okay? So this is a lot, guys. It's like running too much, but I hope you understand all the key ideas. The main idea I want you to remember here is that we have seen how to make a small maneuver in space. We just only increase the perigee of an ellipse 90 kilometers in the example. It's not so much, and it's a very simple idea. But what I want you to remember from this video is I want to calculate how much speed I need to change in an orbit to change the orbit indeed. So it's always calculated with the specific momentum of the orbit that is calculated using the radius of the apogee and perigee, and then calculating the speed at the point you are applying the impulse, the speed in the initial orbit and the speed in the final orbit. So you calculate the subtraction of that and you got the delta V. I hope this is helpful for you guys. Thank you for your attention.